Hello, everyone. Welcome back. I have the pleasure to introduce you to the following module in our deep learning do-it-yourself course. In this course, we'll be going a bit deeper into deep neural networks and see why is it so important that to have these large neural networks. What are those benefits, but also what are the challenges into addressing these beasts practically, to be able to train them properly and in an efficient manner. So this module will be grouped into several smaller chunks, and we'll begin with studying why is it important to have deeper neural networks, and what does this bring with respect to the previous neural networks that we had since so long ago. So just let me start into it. So you might, I guess, although you're new into this area, students, I think you might have stumbled upon into this reaction on thinking of deep learning as just whenever the problem is to have as having this strategy of whenever the problem is more tricky, just add more layers. Well, we know that in statistical learning, we have a lot of heuristics which are grounded into solid maths and statistics, and people seem to know what they're doing. Well, the general impression on deep learning is just okay, to improve performance, you just add more layers. So this is partially true to some extent, but adding then meaning that adding layers in general can improve performance. But there are some good reasons for why this is happening, and we're not just randomly adding layers each time to improve performance. So we'll see why would it be a good idea to stack more layers, and are there any theoretical insights for doing this, or maybe just empirical ones. So this is the subject of study for this module, and what we'll be studying today will be the universal approximation theorem, which kind of motivates the usage of deep neural networks and neural networks in general for several machine learning problems. Then we'll go specifically on why is it good to go deeper, and then we'll go into addressing some of the inconveniences that the depth of neural networks brings, and how we can learn what mechanisms do we have at hand to better regularize and control neural networks. So this is what we'll be speaking about in the next module. And finally, we'll be concluding with arguably the most popular type of neural network architecture, deep neural network architectures nowadays, which is the residual networks. So going on to the deep part first. So a lot of the research in neural networks has been motivating, and the interest in neural networks has been motivating by the fact that they are known to be universal function approximators, meaning that to some extent they can approximate whatever function we might have at hand. So I'll just state the formalisms here and I'll then give you the hand wavy explanations. So this is a theorem from Hornick in 1991. So assuming that we have sigma, a non-constant bounded and monotonically increasing continuous function. So this is actually our activation function. For any f in a continuous domain bounded by 0 and 1, and a certain variable epsilon, there are h real constants vi and bi in R, and real vectors wi, such that when we do this approximation, so this is our target function that we want to approximate, and this is practically the output of a one layer neural network. So this is what it says, that we can actually approximate this function f given these parameters. So this theorem actually guarantees that even a single hidden layer neural network can represent any classification problem, if in which the boundary is smooth. So this sigma, actually the theorem holds for several activation functions, including even the ReLU, which is we've seen that is quite used nowadays. However, this theorem does not inform us about how about good and bad architectures, and not even nor how they relate to the optimization procedure. So it's just like if you want it tells us we can approximate practically any useful function that we can have at hand, but it doesn't tell us how we can get there. So it tells us that it's possible, right? So it glosses quite a lot of assumptions on how we if we can train this, how many neurons, because it can go actually to an infinite number of neurons here, and so forth. So so there are some things that are omitted from this theorem, but it still serves as a good motivation to show that actually we can approximate to reasonable degrees several types of functions. So in a follow-up work, Barron et al. Came up with an additional theorem where they measure actually the mean integrating square error between the estimated network f. So this is what we output. So this is what we train, and the target function f. So this is the objective, which is found in the data, is bounding by this value. So I'll detail some of them. N is the number of training points, so we have a log n here and here. Q is the number of neurons, we have Q in here. P is the input dimension, we have it here. And C, F measures the global smoothness of S. So F, so in that paper, it was taking the moments of the magnitudes of the Fourier in estimators frequencies in the weights of this neural of the F. Sorry, when we do the decomposition in the Fourier, we can compute this global smoothness there for the target function that we want to approximate. So again, this looks like something fancy and difficult to digest, but the take-home messages is that actually providing enough data, this theorem guarantees that adding more neurons will actually result in a better approximation. So then, is this problem solved? Not quite, because this universal function approximation theorem do not tell us what's the ideal number of h of hidden units, such that we the number of hidden units small enough to have the network fit in RAM. Anyway, then the RAM varies from one machine to another. The optimal it doesn't tell us neither whether the optimal function parameters can be found infinite time by just minimizing the empirical risk with the stochastic gradient descent and the normal random initialization scheme. So we don't know if we actually can reach this minimum, if we can actually find the corresponding minimum, right? It tells us tell us we need this amount of neurons, but it doesn't tell us how if we can actually reach them with stochastic gradient descent optimization. So so going a bit more to the hand wavy part now, just to spare you probably the dry maths. So here we can put into place to see how we can actually approximate different functions with ReLU nets, right? So here, well, this is a NumPy code inspired by this Quora post and by the slides of Olivier Grisel and Charles Lyon. So what we do here, we define a ReLU. Right? We saw this in the previous courses and practicals, and we use these ReLUs to define this rectangle. Right? So we define here a space of x's in this interval. So we have between -3 and 3, we have 1,000 points, and we have this function y, which builds a rectangle here. Right? So we have used the 4 ReLUs to obtain a rectangle at this point. So what we can do, actually, we can go even further. So we can find other mechanisms of combining these rectangles, and we can see that we have changed the shape of our output function, right? And say that now I have, well, so here I'm just showing how we can deform this rectangle, but say that we want to approximate a sign, right? So I'm defining here a target sign function in this interval, and I try to approximate it with 10 rectangles, right? So you can see that I start to follow it, although okay, it's not so accurate, right? I'm adding 10 more rectangles, and we can see that already I'm starting to do a reasonably good job in approximating this sign function. So remember, I'm using just ReLU units. So it's a one-layer neural network with ReLU units, right? So if I go a bit further to 50, we can see that the quality of the approximation is ever increasing, and then if I go to 500 points, I have the exact approximation of my target function. So this is just to show you that we can actually do quite a bit of things in approximation with by just stacking these ReLU units. So well, still coming back to the universal approximation. So even if the MLP is able to represent the function, we can still have some problems we can fail in reaching this an accurate representation of the function for the following two reasons. So one is that the optimization algorithm may not be able to find the value of the parameters that correspond to desired function, which is what I was telling you before. And second is the training algorithm might choose the wrong function as a result of overfitting. So if we have actually too many parameters, we might actually end up in a different set of values that will just overfit the train set and will not be useful for actually representing the function that we want. Nevertheless, there are still some empirical evidence that seems to generalize. So we can see, for example, that whenever we simply add more and more neurons, the performance, for depending on the problem, of course, seems to improve. So here we have this semi-moon data set. We have here the red points, the red class, and the blue class, like here. So if you just use a simple classification, a linear classifier, we cannot separate better than that, right? We cannot have a more curvy area because we have just practically two parameters there to define our separation plane. If we start adding more neurons, so here I have a hidden layer with size 3, we can see that I can better capture the boundary between these two classes. And here I have several examples like that, where we can see that as I add more 1, 2, 3, 4, 5, 6, 20, and 50, as I add more neurons, the quality of the separation plane is better. Although at some point you will see that it's starting to overfit. It follows too closely the curve from our training data. To bring you another argument for why having more parameters and more layers is a good idea, there's this folklore experiment proposed by Libni et al. So what they do in step 1, they generate label data by feeding random input vectors into a network of depth 2 with a hidden layer of size n. So what we do here, I take a neural network, I initialize it randomly, and then I take some random vectors, I pass them through the network, and store the activations, the outputs. Right. In step 2, I take another network with exactly the same architecture, but with a different initialization. So what we do here, we use the data, well, the outputs from in the input and the outputs from the previous step as training data, right? So I take these random vectors and I ask this network to output. I train it to output the exact random output from the first network, and then this is my label, right? So I try to train it for SGD for a long while, and actually, what we realize is that if these two networks have the same size, the problem for the second is quite complicated. However, if we just add more neurons or increase the depth of the network, the problem becomes quite easy for the second network. So this is just to say that overparametrization actually, meaning that having more parameters than I actually need, although if you follow traditional machine learning, it doesn't seem like a good idea. And deep learning actually, it has been shown to help in better training in training easier and faster your models, to have more parameters than you actually need. So that's what we've seen in practice, that it's a lot more easier to do that. So going into more concrete benefits of depth. I will start with visualization from this really nice script made by that you can find in this URL here. So the problem here again, it might seem it's quite trivial, but it helps to better understand what we have at hand. So here, well, I'm just waiting it for it to load. Okay, so here the problem is. Okay, while it's loading, I'll show you here. So what's happening in this problem? We have a three-layer neural network, multi-layer perceptron, and what we do here, we have this input image. So in this input image, what we will give as input, this is our training data practically. This image with a bottle in it, with black and white pixels. So what we feed to the neural network is 1 pixel at a time, where we give the location and on the x and the y coordinate, and the output should be 0 or 1, whether it's black or a white pixel. Right. So what we want actually is for this network to learn this bottle and label. Right. So if I give it this pixel here, it should be outputting me a black pixel. If it's not, it will be penalized, and it will go back and forth until it will minimize the loss, and it will be accurately representing this bottle. So yeah, here is my target data, but I'll shift now to the network output. So here on the upper part, you can see the evolution of the training loss in time. You can slide like this. So when you slide, you can see that as I am approaching the minimum, the network actually has learned to reconstruct the bottle. But our purpose is rather to analyze what's happening. So what I'll do here, we can actually visualize separation planes from the first layer. So I'm just showing a few of them here. Just for now, I have just one. Maybe I'll have another one. Yeah. So we can see that I have a few separation planes. So practically each neuron here takes a decision. It practically tells you whatever is at the right is white, whatever is at the left is black. Here, probably this guy says whatever is up is black, whatever is down is white, or the other way around. So these are the decision boundaries that can occur in a first layer, right? So we can see that they're simply lines, right? They're not showing any complex patterns or or anything like that. They're really some simple lines. So I'll go back to the beginning, and let's see now some in red, some outputs from the second layer. So we can see that in the second layer already the separation planes are starting to be different. They're not just a straight line. They're starting to move around and to actually follow the objects. So we can see that. Let me read. So okay. So this neuron 8 here has started actually to recognize the shape of the bottle by itself. You can see. So it kind of tells you whatever it's inside is black, and whatever is outside is white. And we see how it will evolve. Well, so after a while, it seems to be losing it. Yes, it's under the impact of some other neurons. And let's see if it comes back somewhere at the end to it. No, I guess it lost it. So let's find some other neurons that, okay, this one seems to have found the separation plane here at the label. So I have this red one here. It separates this other edge. And I guess, well, this one also tries to separate this other part of the image. But they don't have to be perfect because we're still not at the output, right? So in this part of the network, we do not give any supervision at all. We give the supervision just at the output, right? So this is just the weights moving according to the data. So let's see now for layer 3. Let's find some interesting neurons, right? So we have this neuron. Well, I'll just hide the blue ones. So you can see that this neuron, this green neuron here, has actually again found the shape of the bottle, but we are at the end, so it's more accurate. What else we have? So this neuron here, where is it? 11 has found how to classify just this label in the image. So let's just go back and to see how they evolve in time. So at the beginning, we can see that these neurons are practically, well, do not say much. They're quite fuzzy. Probably they're outside the decision boundaries. And we see as the training evolves, they become tighter and tighter, or they fire onto different patterns that are useful for the classification downstream. Right? And then we have a classification layer on top of these green neurons that will tell us whether it's a 0 or 1. So we can see that actually the deeper we go into the network, the more expressive and expressivity we have in the representations, because they can fire onto more complex patterns, not just simple lines as we had in the first layer, right? So you can see that the shapes are having a more particular shape, a more particular visual aspects. Okay, so this is one. Well, this illustrates graphically why it's good to have deeper networks. And this is again is a simple example to show how much impact we have actually on the expressivity by adding layers with respect to just adding more neurons on a layer. So this is an example from Telgarsky. And again, we are using the ReLU. So we have here the ReLU function, but what we use for now, we define some triangles, right? So we have a ReLU on top of some ReLUs. So with this triangle function of this interval, we define this triangle, which we call it like we can name it an oscillation. If we apply it again, this function on the previous one, right? So we take this output. So we have 3 of x, and then we apply another 3 of x. So it's actually like adding a layer in a network. We can see that we have now 2 oscillations. So, well, so far we can say, okay, we can get these 2 oscillations by just adding, like we did in the ReLU, by just adding another triangle. So it's not much of a big deal. But actually, as we go deeper and deeper, we can see that when we add one more layer, we double the oscillations. Right? So we are more efficient into getting these spikes by using fewer ReLUs, like fewer neurons. And the same as we go even deeper. So we're now 4 layers. We can see that we get more and more oscillations, which allow us to be more expressive and to approximate the function that we wish for better. So so the takeaway message here is that adding the parameters required for one new layer can multiply by 2 the number of local oscillations in the decision function of the model. So we contrast this with the approach of adding parameters on the same layer, making the layers wider, as we saw in the rectangle example, that can only contribute in an additive number of new local oscillations. So what this means actually that we're way more efficient by adding new layers than by with the same amount of neurons than by making our layers wider. And this is a very nice example from Montufar et al. So they made this nice experiment on these two on this data which is like a sign, and inside we have the blue points, and at the exterior we have these red points. So it's a classification problem. So what they do, they use a small neural network. So with the solid, they have a neural network with 20 hidden units. And with the dashed, they have a 2-layer neural networks with 10 units per layer. So this means that both networks have the same number of parameters, but just that one is wider, the solid one, and the other one is slimmer but deeper. Right. So we can see that actually the slimmer one is better in capturing the differences between these, the separation boundaries between these two data points, two data sets. Sorry, because so even though the first one can do a reasonable job, right? If you can see here, we don't see much of a difference between the two of them, but we can at some fine points you can see that it still makes errors, right? For example, here the blue ones should be on the other end of the other side of the plane, and the dashed one gets it right. So that's to say that the deeper the network, the more expressive it is, and in general, if you have to trade off with depth, it's always a better idea to trade with to use the depth. However, well, if you have really quite a bit of parameters, it's worth investing into depth as well. It's just that at some point it becomes also efficient to invest into, given that the network is sufficiently deep, it's worth investing into the width as well. So what we observe in practice is that a good combination of layers and numbers of parameters, number of parameters is key for improving performance. But well, if you did other machine learning courses before, you might know that increasing the capacity, it seems to be going against the findings from statistical machine learning, right? So if you remember from these courses, usually, so if you have here the model complexity, can be also the capacity of a neural network. So we know that in general, the bigger capacity, the lower the training loss. So the lower the training loss, but the higher the testing error. So this means that it's to show that we are overfitting. And this is something which is quite known in machine learning since decades. That we have to get this trade-off into underfitting and overfitting, and also in bias and variance. So that's usual machine learning models, right? With the complexity that has been studied. So I'll let you guess where with the neural networks with their multi-million parameters will be here. Well, unfortunately, I don't have much space in these slides, but they should be somewhere here. And what we've seen that we don't have this, right? We don't, even that though we are here, our testing error is still low, right? And that's why we use neural networks in so many applications nowadays, is that they still have low testing errors for the test cases that we consider. And this is actually quite intriguing. So well, this is a nice plot from Zhang et al, where they analyze the size of the network, right? So we have here a regular MLP. We go to AlexNet, then we go to Inception, and then to a wide ResNet, and it's plotted against the the error on images. So we see that as the network is bigger, the error goes lower. So again, it's contradicting a bit the findings that we had from machine learning from before. And even more than that, they show here the ratio between the parameter count and the number of training samples. So here in a wide ResNet, we have practically 179 neurons per image, right? So we might see, I mean, why doesn't that what could stop these networks just to have one neuron that memorizes image, since anyway we have 180 more neurons than images, right? So again, well, for Inception we have 33 more neurons than images. For AlexNet, 28 more neurons than images. So this actually has been quite intriguing in this deep learning revival surge area. And there were several people with more theoretical backgrounds that analyzed this pattern. And actually, this led to a finding, which was published last 2 years ago now, by Belkin et al. That have noticed this double descent curve. So this one is what I presented before, right? So which is the findings, regular findings from machine learning, where the bigger capacity, the lower the risk or the error, and the bigger the test risk or the test error, right? So this is the overfitting. However, what Belkin et al. Had studied, so they swept to, they trained, well, on MNIST mostly, but they train a lot of models by always increasing capacity by a bit, and looked at the pattern. So what they noticed is that indeed, if you take a model and increase the capacity, until a certain point, you notice what we were noticing also in previously, historically, that we were before underfitting, and then we were overfitting. But then as we continue to increase the capacity, we have another descent. So we descend and we go up, and then we have another descent, and the test loss goes down again. Right? So the bigger the model, the lower the loss, actually. So and actually this kind of reinterprets what we knew so far. Likely, well, people didn't go beyond until now we couldn't go to these high capacity models that fit. We didn't have GPUs and other large scale computing powers to facilities to train these big capacity models. And well, it's actually that we didn't know. right? So we didn't know that we have this this double descent, but well, thanks to the study by Belkin et al., we actually know of this double descent, and this actually doesn't generalize also to just neural networks and deep neural networks, but they show it on some other algorithms like this, like decision trees and boosting trees, that we have the same behavior. I mean, the bigger you make the trees and the bigger you increase the capacity, you get to practically the same behavior of this double descent curve. And here I'm showing some example on their experiment with MNIST, where they have a fully connected neural network with two losses, 0,1 loss and a squared loss. This is a train loss that goes down like that. And we see that at some point, at 40,000 neurons, in both cases, they overfit is the critical point, and there they once we go bigger capacity from there, this test loss goes back down again, and as you can see, it's better than the minimum we had before. Right? So if we have done early stopping, if we have stuck to this type of parameters, this amount of parameters, we couldn't have gotten to by fear of not overfitting because our model would be too big. Actually, we'd have missed this good performance in the test. So this is just to say that okay, there's quite a few benefits in having deep neural networks and over-parameterized neural networks. Unfortunately, there's not just benefits. There's also some inconveniences to address, and we'll see in the next module what they're about and some solutions for doing that. Well, thank you, and see you in the next module. Bye bye.